Test? Too loud? No, it's okay. What if I yell?
That'll be too loud.
Okay, I'll try not to scream. Oh, cool. Lamont time or Caltech time?
Exactly.
Or Hebrew University time? Yuri, how long is it?
It's usually like 45 minutes
Okay,
long.
perfect. Perfect. Awesome. I tend to talk over always, so feel free to just take this and start beating me on the leg if I go long. Yeah. Cool. Yeah, of course. Oh, I'll just self-introduce. Hey, everybody.
Okay, we're running a few minutes late, but when Ron gets here, we'll start. Oh, it's here.
so Jesse's one of the most passionate oceanographers I know. If he's not in the lab doing boron isotopes or something, he's on the surfboard, right? The rumor is that he actually made the waves of the reef look surfable yesterday. So he started his academic career at Brown, which in kind of a weird way has become one of the best places for undergrad oceanography, paleoceanography. Past 20 years, a lot of leading oceanographers came out of Brown. I don't know how that happened, but
John Embry. Yeah.
But right, from Embry's Boaz Luz, right? And a long time ago. Anyway, then he went to work at the USGS with Tom Cronin on Arctic sediments. Then he moved to Lamont to work with Greg Wahonish on boron isotopes. He did his PhD there. Whereas this is where I met Jesse. Jesse was a year older than I was in the program. And it was very clear from the beginning that he was sort of the benchmark. Like this is what you want. This is what a paleoceanographer looks like. If you want to do something like that, you have to. Right? Jesse knew everything, knew what was going on, knew what the big questions were, right, and sort of pushed through it. It's true. It's true. So that was. And if you look at Jesse's PhD, it's kind of cool because he worked on this massive variety of things, right? So he started off with trying to figure out how the nitty-gritty instruments work. Why is there a problem with boron isotopes between TIMS and an Neptune? Right? So he played around for, 2 years trying to measure the same samples on both, trying to figure out. That's sort of on one scale. On another scale, he asks us how the world shifts from 41,000 year cycles to 100,000 year cycles. Right? So a really big array of types of questions that Jesse asks. And everything in between, including bamboo corals in the Arctic, things like that. So that was his PhD. And then he did his PhD right at Lamont. Greg Wahonish, his committee was Jeremy McManus, Peter Domenico, one of the biggest paleoceanographers in the world. Where did you go from there? Like, how do you step up from there? And the only real place to go was to work with Danny Sigmund and Gerald Haug, right, on nitrogen isotopes. So Jesse's been doing his postdoc for a bunch of years now, not because people don't want him, but because he has to stay in a very specific geographical location, but now he's got a position in Boston, so he's finally finishing his postdoc. So Jesse, take it away.
Thanks, Yoni. Wow, that's one of the better introductions I've ever had. I think I need Yoni to be my hype man and write my applications for me. In reality, I'm like a tortured paleoceanographer. I had to work on boron systematics for a while. I was like, can we do paleo? And I had to wait and learn the whole system. But anyway, thank you all so much for coming both in person and virtually. The acoustics are a little weird. I like to talk loud, so I'll just try to pull my shirt down so the microphone's not too loud here. So I'm really excited to talk about, in my first visit to Israel ever, which has been fantastic for the last 10 or 15 days now, to come up here and give a seminar is just the icing on the cake. So thank you all very much. I'm going to talk about one aspect of my postdoc work with Danny Sigmund, Gerald Haug, Alfredo Martinez Garcia, and others, which kind of gets back to a big question that paleoceanographers spend way too much time thinking about, which is how have these gateways changed in the past? How have these ocean gateways changed? And I'm going to take a really weird tool and a weird approach, but try to convince you this is a really promising approach to look at gateways, and that's using the marine nitrogen cycle. So this photo here is of the Bering Strait. This is far eastern Siberia. This is far western Alaska, about 100 kilometers across between these two continents. And this will play a big part in the second half of the talk. So if you're interested in the Bering Strait, hold on, I'll get there. Before I begin and show you some data, I want to thank just so many people who have been part of this project. And I don't have time to name everybody here, but I want to just point out a couple. Tamara Pico at the top left, who's an assistant professor at UC Santa Cruz. She's a sea level modeler. She did her PhD with Jerry Mitrovica. And we've found common cause on trying to understand the sea level history of the Bering Strait, which you'll see in the second half. Some awesome undergraduates that have worked both with myself and with Tamara. Ona Underwood, who was at Princeton, did her undergraduate with me working on both the Arctic Ocean and also the Southern Ocean, because one pole is not enough. Becca Cleveland Stout, who is working with Tamara at Harvard on the sea level component of the Bering Strait. Antia Arns, who was an undergraduate at Max Planck and is now getting her PhD at ETH. And of course, Danny Sigmund, who is not a PhD student anymore. And then one last person to really call out here is Gerald Haug down here. Gerald's been fascinated with the question of ocean gateways, and particularly the Central American Seaway, for pretty much since he was a postdoc. And he provided a lot of motivation to think about using nitrogen isotopes as a tool to look after these gateways in the past. Also, am I talking too quick for anybody? No, it's okay? All right, I like to talk fast, so I have a lot of slides, but interrupt me and slow me down if I get off the rails. So just as a quick outline here, I'll give a background on ocean circulation gateways. Why do we care about this question? I'll introduce the concept of using the marine nitrogen cycle, essentially the nutrient cycle, the key limiting nutrient, the cycle of that nutrient in the ocean as a tracer. I'll then talk about this in two themes. The first, the Central American Seaway, the closure of the Isthmus of Panama sometime in the Pliocene, say around 4 or 5 million years ago. And the second one, on much shorter and colder timescales, the Bering Strait, that is ephemerally opened and closed due to the growth and decay of large ice sheets in the Lake Quaternary. And finally, end with some conclusions and future work. Okay, so just as a background, this is an extension of Wally Broker's Great Overturning Conveyor, a little more detailed, a little more nuanced, a little more realistic look of what the global overturning circulation, or the movement of waters between the surface and deep ocean looks like. It's a figure from Lynn Talley. There's a lot of colors going on. Just the colors from purple are the surface waters, red are sitting underneath the surface waters, yellow are sitting underneath the red waters, green sitting underneath the yellow, blue sitting underneath the green. So this is color-coded by depth in the water. And fundamentally, this is the circulation. This is the movement of waters and their associated climate variables, including heat and uptake of carbon dioxide, throughout the global ocean as it exists today, in today's world. And we care about this quite a bit from a paleo perspective because we're talking a massive quantity of potential heat storage in the ocean, as well as a massive quantity of potential carbon storage. So when we think about climate change in the past, we care a lot about how this circulation might have changed in past climates. And just to give you an example here, to make this a really simple kind of dance of two variables in the ocean, whenever you've got purple going to green, you have waters that are surface waters that are cooling. That heat release is added to the atmosphere that warms up the atmosphere. But as those waters are cooling, they're also taking up carbon dioxide from the atmosphere and sinking down into the deep. And you can reverse this whole trend as well too when these deep waters in green upwell and turn back into surface waters. They're now cold waters at the surface that can take up heat from the atmosphere, so to cool down the atmosphere locally, but then they also release CO2 as well. So on this sort of millennial timescale that this whole conveyor turns around, we've got this intricate dance between, on the one hand, heat uptake and heat release, on the other hand, greenhouse gas uptake and greenhouse gas release. And this is why we care, in a nutshell, this is why we care so much about overturning circulation or ocean circulation in the past. But one thing I want to point out about this, and it does not pop out here at all, it's so obvious that you probably haven't thought about this. Anywhere that these arrows go, of course, it's limited by where the continents are placed, right? So you can't move the ocean through the continents, of course. And one of the things I like to think about is, well, what does ocean circulation look like as the continents have moved over geologic time? And so if this works, all right, so we're going over the last 500 million years plus here. This is way longer timescales than I currently think about. But just consider, today we've got deep waters forming at the high latitudes, essentially where it's coldest. And sort of, when I look at this map, I mean, obviously understanding the position of the continents and the climate changes associated with that is important. I look at this from the perspective of where the blue is and how the ocean might have operated in those different plate tectonic configurations. And so we might think of deep waters at 350 million years ago forming in the high latitude northern hemisphere, perhaps taking up CO2 as well too, releasing heat back to the atmosphere. But fundamentally, as all these continents are moving around, whatever ocean circulation we can fit to that continental regime will be dictated by where the continents are. And what this leads to, and something that I won't let this movie go all the way through, I think you know how it ends with our modern configuration, but there's the opening and separation of ocean basins that's happened over geologic time. So we have a basin right here that did not exist just 50 or so million years ago. We're starting to see the Atlantic open, the proto-Atlantic open around 100 million years ago. All these connections, loss and gain of connections, change the way that the ocean circulates around the world and thus change the way the ocean might have taken up carbon dioxide or regulated greenhouse gas concentrations in the past. And just picking a couple of these, there's a lot of gateways that matter, but as paleoceanographers, we've identified 10 or so that particularly matter over the last, say, 100 million years. And I'm certainly not going to go through all of these. I just want to focus on two of them in particular. One, the Central American Seaway here, as I mentioned before, is currently a land connection between North and South America. It was not that case going back into earlier in the Cenozoic. And the second being the Bering Strait, this very shallow connection but separating Asia from North America today. So the tool I'm going to use to interrogate these two gateways in the past is based on the marine nitrogen cycle. This is a very, very simple cartoon of what's happening in the marine nitrogen cycle. We know there's a lot of processes that matter, but fundamentally of the surficial nitrogen cycle today, the vast majority is N2 gas in the atmosphere that's effectively not bioavailable, with the exception of particular microbes that have evolved the ability to break the triple bond in dinitrogen gas and fix that nitrogen into ammonium. Once they fix that nitrogen into ammonium, they then can incorporate that bioavailable nitrogen into their organic material or into their tissues. This is fundamentally the source of nitrogen to fuel production within the ocean, is this nitrogen fixation. This organic nitrogen then goes through a lot of interconversions. It gets microbially oxidized to inorganic nitrogen, will get fixed back again to organic nitrogen, back and forth, back and forth. Eventually, the nitrogen that's fixed or bioavailable within the ocean will be lost by the process of denitrification, where in this case it is reduced back to N2 gas and escapes back into the atmosphere. So these two processes, the input term, the nitrogen fixation, the output term, denitrification, they're not co-located in the ocean. And this is very important for considering gateways. To give you a flavor of what this looks like, this is a model study by Wang et al. That tried to take into account where nitrogen fixation is happening in the ocean based on the green colors here. The darker the green is a higher rate of nitrogen fixation. And conversely, where denitrification is happening within the water column, where fixed nitrogen is being lost from the ocean and escaping back into the atmosphere. And the main thing, there's a couple points to be made on this, and isotopes will come next, so let's just think about concentrations for now. Anywhere nitrogen fixation is happening, that's going to be adding new nitrogen in the system, will be increasing our concentration of nitrogen. Where denitrification is happening, conversely, we're losing that nitrogen, so we're removing nitrogen from the system. Now, these are not co-located, as I mentioned before. In particular, you can find that the highest areas are the reddest colors here of water column denitrification. If you think about oxygen in the ocean, this looks very similar to oxygen. These are the oxygen deficient zones in the eastern tropical North and South Pacific, as well as the Bay of Bengal and the Indian Ocean. But there's also a component of this that's the global overturning circulation as well too. So just looking at the Pacific Basin as a whole, we see higher rates of water column denitrification, or stronger reds here in the Pacific versus the Atlantic, where there's really not much water column denitrification happening. And that's in part because we're forming a lot of deep water in the North Atlantic that's well oxygenated. There's just too much oxygen for this denitrification process to happen. And I don't think I said, but I should have said, denitrification occurs because microbes switch from using oxygen as their terminal electron acceptor to using nitrate. It's the second biggest bang for your buck in terms of energy if you're trying to get an electron acceptor. But the big takeaway here is Atlantic Ocean doesn't really have much loss of nitrogen, whereas the Pacific Ocean does. So there's a fundamental basin scale difference in our loss terms here. In terms of inputs, it's not fundamentally that different between the two. So it's the loss that's going to matter quite a bit for thinking about how the ocean gets separated into basins based on its nitrogen chemistry. Okay, so we have to do some isotopes, but I'll keep this very simple. Everything I'll talk about in terms of isotopes in delta notation, delta 15N, which is our nitrogen 15 to 14 ratio, our two stable isotopes of nitrogen, in a sample relative to our standard. Standardization for nitrogen is super easy because we've got this massive 71% of the atmosphere that we can use as a standard. It's isotopically homogeneous. And what I'm plotting here on the right, a figure from Sigmund and Frippiot, nitrate concentrations in the ocean versus the isotopic composition of that nitrate in the ocean. And we're starting here at our kind of mean ocean value today. This is just a thought experiment. So we have about 30 micromoles of nitrate in the ocean sitting at around a 5 per mil isotope value today. If we add more nitrogen to the ocean, say we can somehow just ramp up nitrogen fixation, we're going to move in this direction. So we're moving mostly to the right. Of course, we're adding more nitrogen, so our concentrations are increasing going to the right. But the nitrogen we're adding also has a low isotope ratio. It doesn't have as much 15N as 14N. And so we're not only moving to the right, we're moving down here. So we're adding nitrogen, but we're also adding isotopically light nitrogen. Conversely, if we lose nitrogen from the ocean by water column denitrification, we're losing nitrogen, so we're moving to the left here, our concentration is decreasing. But there's a very strong isotope effect of water column denitrification because microbes prefer to use the light isotope here and strongly prefer in the case of denitrification. So for just a small change to the left, a small reduction in concentration, we have a really big isotope effect. As water column denitrification ramps up, we see a higher and higher delta 15N or a higher isotope ratio of the nitrogen that remains within the ocean because the nitrogen 14 is being preferentially used. You're not all asleep yet, so I hope this is...
No, I just wonder why.
What's that?
Just wonder why. Why do the bacteria prefer N14?
So my understanding is it's an enzymatic process, and so the kinetics of that enzyme will convert nitrate back to N2 faster with nitrogen 14 versus with nitrogen 15. So it's just a kinetics of that enzyme reaction. There's probably a more detailed answer. I'm sure there's a more detailed answer. There's probably some more nuance there. Okay, so what I'm showing now is an assimilation model, and the colors up here, of the isotopic composition of nitrate, blue being the cooler colors being lower delta 15N, warmer colors, reds being higher delta 15N. And this is at the subsurface, so we're sitting below the mixed layer in the ocean, looking at how the isotopic composition of this nitrate that can get upwelled to the surface changes over time. We're not looking at the surface because, of course, if we look in the surface, we're going to see the effect of assimilation, in this case, organisms preferentially taking up light nitrogen nitrate versus heavy nitrogen. So this is essentially, you can think of this as the source waters, or the source nitrate that fuels production. We're comparing this against this map of water column denitrification rate. And hopefully you can see there's quite a bit of similarities. You can see the ODZs, the oxygen deficient zones, very high nitrate delta 15N, same regions where we have high denitrification rates, same in the Bay of Bengal. And conversely, in the Atlantic, we see much, much lower nitrate delta 15N, about the lowest we find anywhere within the subsurface ocean today. And again, this is because, in part, there's a nitrogen fixation happening here, but there's really no significant water column denitrification. So there's no way to take these values and move them up. And so we're stuck in this blue area in the Atlantic. And of course, I look at this as someone as a paleoceanographer and geologist, like, this is a massive signal. The Atlantic's 2 per mil or 3 per mil. The Pacific's something like 8 to 10 per mil. There's a gateway that used to exist here that's no longer there. Signal to noise is the fundamental problem of doing paleoceanography or any isotope measurement. If you can give me a 6 or 8 per mil signal, I can be terrible in the lab and still measure that, right? Bering Strait, there's actually an even bigger isotope gradient across here. You don't see it at 250 meters, but I'll show later on in the talk how big the isotope difference is of nitrate between the Bering Sea side and the Arctic side. Okay, now this assumes that we have a way to kind of get after these themes. We need a way to be able to reconstruct this spatial pattern, or this nitrate delta 15N. That's not an easy thing to do necessarily. We don't have necessarily... Well, we have tools that we can measure nitrogen isotopes in, but we have to be concerned about diagenesis and other factors. So the way we do this, and this is techniques invented in the Sigmund lab by Abby Wren and others back just about 10 or 12 years ago at this point. This is a foraminifera, heterotrophic zooplankton. It's not this big, okay? It's about the size of a head of a pin, and it makes a calcium carbonate shell. It's a very ornate form. This is a rock, in other words. This is just calcium carbonate. But the reason it has one of the reasons it has such an ornate shell, or an ornate form to it, it's not just a spar, so if we zoom way, way in on the shell, what we find are layers of organic material inside of it. So if we're zooming way in here, you can see these lighter layers here. This is actually a different foram. I think that this is Jonathan's work. You can see these brighter colors as well too, indicating the presence of carbon, nitrogen, and phosphorus. In this case, being the presence of bands of organic matter within a foram. So what we do in the Sigmund lab is we take 1,200 or so of these, no big deal. We put them all in a vial, we clean them with an oxidative solution, to remove any organic material that might be hanging out on the outside of the shell, or any organic material that's not inside the shell in these little bands. We then do some sort of Frankenstein chemistry with nitrogen. This is fundamentally just redox chemistry. We first, we dissolve all these shells, which liberates this organic matter into solution. We then oxidize the solutions to convert the organic nitrogen into nitrate, its oxidized form. We then have nitrate in a solution. We feed that to a denitrifying bacteria that converts it to N2O gas and measure that N2O gas on a mass spectrometer. It's pretty wild. One of the reasons I started working with Danny is when I read the methodology for these papers, no way. There's no way this works. For those of you that work on isotopes, anytime you don't have 100% conversion, there was a guy named Sir Walter Rayleigh who said, you will have crazy big fractionation if you don't get 100% conversion. And we spent a lot of time ironing out this method in the lab that every single one of these steps we get 100% conversion. We standardize every one of these steps starting from the shells themselves. We have a coral standards that we run. We have organic standards, so we have the solution oxidized. We have nitrate standards, and we have N2O standards. We standardize every part of this process because we're so concerned about not getting that 100% recovery. Now, fortunately, work that Abby Wren and others had done, in this case about 10 years ago. On the x-axis here, you probably can't read it. This is the subsurface nitrate, delta 15N, the colors on that map that I showed you on the previous slide. And on the y-axis here is the isotopic composition, or the delta 15N, of the organic matter within the foraminifera. And these are core tops collected throughout the ocean. Fundamentally, what we find is there's a strong relationship between our foram-bound delta 15N and our subsurface nitrate delta 15N. In other words, we can use these foram-bound measurements as a proxy for how the subsurface nitrate isotopic composition changed in the past. Okay, so the first application of this is to the Central American Seaway. Something like 35 million years ago, it probably didn't look like this, to be honest, but ask anybody, you'll get a different answer. There was a pretty significant gateway, but connecting, in this case, the tropical Atlantic with the tropical Pacific. We know from modeling experiments that if you make a gateway here, what happens fundamentally is even though your wind stress is acting from, in this case, from east to west, your net transport is across the strait going from the Pacific towards the Atlantic. That's been true in every modeling study of having an open Central American Seaway. And of course, that doesn't exist today. There is no low latitude connection between the Pacific and the Atlantic. So how do we know when this seaway closed and when we had the formation of the isthmus? This has been worked on for a long time. You can think, there's a very easy, not easy, but there's a non-ocean way to look at this, which is when do you have terrestrial, similar terrestrial flora and fauna in North America and South America? That's one way to get a time. Some interesting, more paleoceanography work by Lloyd Keigwin done back in the late 1970s. This is time moving forward from 6 million years ago to 2 million years ago. And here plotted is the oxygen isotope composition of these foram shells. In the black, the filled circles is the Atlantic, the open circles is the Pacific. And what Lloyd saw is a divergence between the Pacific and Atlantic sometime around 4 million years ago, suggesting, at least from an ocean perspective, the Central American Seaway had cut off the Atlantic from the Pacific around 4 million years ago. Now, if you talk to the geologists that actually work down here, they'll tell you it could have been something more like 12 million years ago that the seaway first opened. Depends on your perspective. And this is kind of a frustrating problem in the sense that I'm putting together every observation here. This is from a nice review paper by Aaron O'Day in 2017. Pretty much every kind of ocean-related observation we can put to see when the Pacific and Caribbean separated from each other. Or in other words, when the Central American Seaway closed and Panama as an isthmus separated those two basins. So I'm not going to go through this in detail. Also, it's annoyingly the time axis changes on all these plots. So I would not have made it this way, but whatever. I just want to introduce what these tools are. So these two are looking at the composition of reef species in both the Eastern Equatorial Pacific and the Caribbean on either side of the Isthmus of Panama. This is the preservation of carbonate within the deep ocean in the Pacific and the Atlantic. This is a much, much higher resolution version of those oxygen isotopes that Lloyd Keigwin did, the Pacific red, Caribbean and blue. And then this is neodymium isotopes in the deep ocean, looking effectively at how deep ocean waters are separated from each other. If we just take all this together, there's a lot of work done here, and I don't want to disparage the work that's been done, but it's kind of hard to put any of these tools together as the sort of obvious signal of a separation of the Pacific and Atlantic. The most cited one, I think the most used one, is this oxygen isotope record in 4Ams, arguing for fundamentally a change in salinity, a salinification of the Caribbean, where the Pacific did not see that around 4.1 million years ago. And this is a really important record. But as those of you that work on oxygen isotopes know, there's a lot of other variables that could be at play here. One that's been cited is that once the Isthmus of Panama formed, there was a diversion of major rivers in northern South America. They might have brought, in this case, more fresh water to the Pacific and cut off the Caribbean from river inflow. And just to give you a sense of the flavor of the debate about this, I want to read just a small passage from Peter Molnar, who's just a wonderfully skeptic paleoceanography critic on this. So I challenge the assumption, if not deduction, that the closing of the Central American Seaway was necessary for the climate change leading to the waxing and waning of ice sheets in the Northern Hemisphere. Lest it not be obvious to casual readers, let me state that the closing of the Central American Seaway seems to be no more than a bit player in global climate change. Quite likely it is a red herring. Two things here. One, paleoceanography is a pretty small field. We don't usually take massive shots at each other like this. This is about as contentious as it gets in paleoceanography, at least what I've seen. But the other is, what Peter's taking issue with, and I completely agree, is that given all the observations we have, if we're not sure about when the seaway closed, how can we possibly ascribe any of the climate changes that happened on Earth to the closure of the seaway? And that's a very good point, and I agree with Peter on that. If we need other constraints to say when the seaway closed. Okay, so I'm going to use the exact same cores that were used for oxygen isotopes to define the closure of the Central American Seaway, and I'm just going to measure nitrogen isotopes in this 4M-bound organic matter instead. One thing to keep in, so this is 999 in the Caribbean, 1241 in the Pacific. One thing to keep in mind is where the subsurface nitrate is coming from is very different in the Caribbean and in the Pacific. And this is because there's a much deeper thermocline within the Caribbean today. This color code is nitrate concentrations. The little lines are temperature surfaces. So high nitrate concentrations are really only occurring under about 200 or so meters within the Caribbean, whereas they're more like 50 meters within the Pacific. And this gets into another big debate in paleoceanography. How has the water column changed in the eastern equatorial Pacific? I won't go into that in detail, but this will matter a little bit. Okay, here's all the data. LRO4, benthic 018, I'm working in the Quaternary, so I'm required to show this by law. Got time moving from 5.3 million years ago to 3.2 million years ago, time moving forward to the left. Here's the oxygen isotopes in planktic foraminifers, the same data that you saw before. Orange is the Pacific, blue is the Caribbean. And then on the bottom, here's 4M-bound nitrogen isotopes, all unpublished data, please don't scoop me, from the Pacific as well as the Caribbean. These solid lines, each individual data point is a diamond, and the solid lines are 100,000-year moving averages to these data. So a couple observations. One, you can see the really strong, and I've shaded here, the strong divergence of oxygen isotopes around 4.1 million years ago. At that same time, two things, let me step back. One, the Pacific hasn't really fundamentally changed in its mean state of its nitrogen isotope value between 5.3 and 3.7 million years ago. We don't see any evidence. The Pacific isn't rising, declining. There's variation, of course, but staying flat. In contrast, the Caribbean has a decline, essentially a two-stage decline in it, but particularly between about 4.2 to 4 million years ago. And after 4 million years ago, we're essentially staying flat like we were in the Pacific. I'm ignoring orbital scale variability. We know that the marine nitrogen cycle is dynamic on orbital timescales. Just focusing on the sort of long-term or what I think to be the tectonic trends here. So fascinating. There's a separation of the Caribbean delta declines while Pacific does not. At the same time that planktic 018 separates between these two basins. I want to go a step further, and I'm going to move through this quickly just for time. One of the kind of annoyances to me of the Central American Seaway question is it's hard to get quantitative data out of the paleo observations. And so what I want to do with the nitrogen isotope records is come up with the world's simplest one-box model for nitrogen isotope change in the Caribbean Sea. It's so oversimplified, it's almost funny compared to what we typically do for nitrogen isotopes. But I would posit that it's important to have an incredibly simple model here. We're working 5 million years ago. We don't have that many constraints about the fundamental inputs and outputs of the nitrogen cycle. So let's keep this very simple. So if we consider this is actually something like we would do for epsilon neodymium in deep ocean mixing. We've got nitrogen isotopes in the Caribbean Sea, a nitrogen isotope composition of nitrate, recorded by our, in this case, our blue delta 15N values. We've got an input of nitrate from the Pacific that's recorded by these orange delta 15N values and assume a concentration for that. We've got another input coming from outside the Caribbean Sea in the Atlantic, and we're assuming both the delta 15N and the concentration of this. I will say this is a big assumption, right? I'm aware of this. I'm working on another core. I'll measure this when I go back to Princeton in 2 weeks to essentially not assume this value, to be able to plug in another record to constrain what the Atlantic end member is doing. But what we can do with this is just fundamentally solve for this orange arrow. What fraction of Pacific delta nitrate is entering into the Caribbean Sea? And we propagate uncertainties both in our measurement and in assuming these different concentrations and isotope ratios. Here's the fraction Pacific, and it's probably not surprising. It looks like the Caribbean delta 15N record. So we see something like a maximum of about 25% nutrients sourced from the Pacific entering the Caribbean Sea, but then a very sharp decline in that to no nutrients from the Pacific entering the Caribbean Sea after 4 million years ago. Okay, I'm gonna skip this last part. We did some fun experiments in ESM2G with people at GFDL, a really high resolution simulation in different configurations of the Central American Seaway. This is all work that Laurie Sentman did. They're really fascinating work. It's a really cool observations. Fundamentally, what happens is when you go from having a wide or almost a 2,000 meter deep gateway to a shallow one, 2 things happen. One is and this is depth here, this is transport, Atlantic is to the right. I was going to skip this, but I think this is important. If you go from a deep gateway to a shallow gateway, within the shallow realm, you intensify your transport. And you can kind of think of this like squeezing a garden hose. If you squeeze on a garden hose, the velocity of that flow increases.
Not the transport.
Sorry?
But not the transport.
So not the integrated transport overall. Within the upper water column, the transport increases, but there's not enough extra transport within the shallow part of the water column to compensate for all the transport you lost at depth. And so the way we think about this is that as you shoal the seaway, and of course this is only 2 experiments, one at a 200 meter deep seaway, the other at 2,000 meter. As you shoal the seaway, you're squeezing the garden hose. You're intensifying the transport where you still have a seaway, but not to a sufficient degree to counteract the loss of transport by the shoaling of the seaway. In other words, you're turning the tap for your garden hose off. I don't even know if garden hoses are a big thing in Israel. I guess water is kind of a concern, but hopefully this is an analogy that makes some sense. Okay, so takeaways from this. We find a decline in our foreign-bound nitrogen isotopes in the Caribbean Sea from 4.3 to 4.1 million years ago that parallels the emergence of an oxygen isotope gradient between those 2 basins. Using the world's most simple one-box model, we argue for a cessation of Pacific nutrient input to the Caribbean by 4.1 million years ago. And I would argue that requires that the Central American Seaway was shoaled to at least 50 meters, if not shallower. I'd effectively, honestly argue that because the nitrogen isotopes and the oxygen isotopes co-vary as well as they do, we would expect the oxygen isotopes to reflect very shallow surface water transport. I would argue that by 4.1, you pretty much lost the Central American Seaway, as far as the ocean's concerned. I can't rule out an ephemeral small gateway, some shallow connections, but nothing with enough transport to really fundamentally change the ocean basin perspective of waters being moved from the Pacific to the Atlantic. And so then the kind of takeaway from this is that, well, if it's true that if you believe my argument that the Central American Seaway was effectively closed by 4.1 million years ago, you can't really explain any climate changes after 4.1 million years by calling upon a closure of the Central American Seaway. This is not, you don't need a PhD to make this argument. This is kind of just basic logic. And a lot of the big question with the Central American Seaway is to what extent was it involved in the intensification or the onset of Northern Hemisphere glaciation around 2.7 million years ago. I find it very very hard to believe that the Central American Seaway had anything to do with that climate change. Okay. 15 minutes for the Bering Strait. So let's completely change gears. Let's get colder and let's just focus on the last 50,000 years. So you saw this photo at the beginning of the talk. This is the shallow Bering Strait separating Asia and North America. And the Bering Strait's really cool because it fundamentally has this duality that we know existed. So we've got the modern Bering Strait. This is a bathymetric map of at most 50 meters water depth, or 53 meters at its deepest trough between Asia and North America. And you've got net transport of waters, about a surge up of transport between the North Pacific into the Arctic Ocean. But we know for sure that as we went back to the last ice age, the Bering Strait only 50 meters deep, global sea level decline on the order of about 120, 125 meters. This was not an ocean gateway, this was a land bridge. And you probably learned about this in middle school or the equivalent of this is how humans made it to North America for the first time. There was a land bridge here and they just walked across it. So how do we know the sea level history of the Bering Strait? Well, the typical approach has been take something like a relative sea level record for the globe, or assumed for the globe. This is Elko Rolling's work from the Mediterranean in the Red Sea. And we know the still depth of the Bering Strait, something like minus 50 or so meters. Anytime the Red Sea sea level suggests lower than minus 50 meters, the Bering Strait was closed. Anytime it's higher than 50 meters, the Bering Strait's open. It's a reasonable argument to make, but fundamentally we don't know to what extent this sea level curve is representative for the Bering Strait region. And ideally we'd have a tool that could tell us whether or not the Bering Strait was an ocean gateway or a land bridge. So of course the obvious thing to do is use nitrogen isotopes, right? Let's use a nutrient tracer to look at what's happening with sea level in the past. Makes perfect sense. It's exactly what Yoni and I learned to do at Lamont. No, it's not. This is wild, right? Okay, what I'm showing here is a map centered on the North Pole. Each one of these diamonds is a subsurface nitrate delta 15N measurement. So the color code, blues being a lower isotope value, yellows being a higher isotope value. So what we see is we've got these low isotope values in the North Atlantic sitting around 5 or so per mil. Again, for the same reasons I talked about at the beginning, there's no water column denitrification happening up here, so there's nothing to raise that isotope value. And we can trace these low delta 15N nitrate into the Arctic Ocean following the lines of Atlantic circulation. But then when we move to the Western Arctic, there's a really, really sharp gradient between this. And we start seeing these really high values. And in fact, we can trace these high values back into the subarctic North Pacific and the transport of waters across the Bering, or transport of waters with their nutrients across the Bering Strait from the Bering Sea into the Arctic Ocean. So fundamentally, nitrate within the Arctic Ocean is a source indicator. It's isotopically tagged by whether that nitrate came across the Bering Strait or came from the North Atlantic. And I'm a paleoceanographer, and so we've got some sediment cores that we can use, measure foreign-bound nitrogen isotopes going back in time, and effectively test for the presence of this high delta 15N nitrate. Feel free to ask me why there's a big difference between the two. I talked about this a little bit early on. There's some interesting dynamics that happen on the shelves of the Arctic, but I'll skip this for time. Okay, 4 sediment cores, I just mentioned this. 3 from the Western Arctic that see this high delta 15N nitrate today. 1 essentially from the North Pole that does not, and we don't think it ever saw these specific waters. Each of these cores has an independent radiocarbon chronology, and we're just going to measure foreign-bound nitrogen isotopes within Pachyderma, which is conveniently essentially the only planktonic foram in any abundance in the Arctic. So I don't have to worry about different species or anything, it's just one species. Okay. Last 50,000 years of data shown here, present day on the left, 50,000 years ago on the right. The circles that are colored yellow, orange, and blue are the 3 cores from the Western Arctic. The gray diamonds here are from the Central Arctic. So let's just work back in time. In the last 11,000 years, we find that the Western Arctic has been isotopically elevated relative to the Central Arctic. Before 11,000 years ago, it gets weird. There's a very big decline going back in time or moving forward in time. There's a very rapid rise in foreign-bound nitrogen isotopes in the Western Arctic. We don't really see that as much in the Central Arctic. We essentially find exactly the same values for the Western and Central Arctic between about 11 and 35,000 years ago. And much to our surprise, we see a resumption or reversion to the Holocene pattern before around 35 to 40,000 years ago in all 3 of our cores, with as high or higher delta 15N values in the Western Arctic cores and no elevation in the Central Arctic cores. Now we know this independently, that 11,000 years ago, this is the date of the final flooding of the Bering Land Bridge and the opening of, in this case, the Bering Strait. And we see, this is a paper in 2021, or was that, we're 2022 now. So last year in Nature Geoscience, we had this last 30 or so thousand years, and we said, hey, look, this is the flooding of the Bering Strait. Very rapidly after the Bering Strait flooded, you see this high delta-59 nitrate moving its way back into the Arctic Ocean. One thing I'll say too is that these records are sampled at 1 centimeter resolution. So I'm taking every centimeter of sediment and measuring foreign-bound nitrogen isotopes. We know that bioturbation is a thing. It's probably on the order of about 3 centimeters. I mean, just trace this. That's 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. Within 4 centimeters, we see a 4.5 per mil foreign-bound delta-15N elevation. And conversely, similarly going back in time, 1 centimeter, 2 centimeter, 3 centimeters. 3 centimeters of sediment, that core goes from having a high delta-15N to a low delta-15N. This is one of the wildest paleoceanography records I think I've ever had a chance to see. There's something of a joke coming from Lamont that I like to work on square waves only. I don't do anything sort of orbital scale. It's just like, if it goes from this to this to this, I'm not the sharpest tool in the shed. So this is a very easy interpretation, right? The obvious interpretation is whatever was happening in the Holocene, namely the Bering Strait being flooded, was also true before 35,000 years ago. So when I first got these data, my reaction was no way. Because I went to Lamont, I got to learn from sea level experts like Mo Ramo, and there's no way in my mind that sea level could be high enough during stage 3 to flood the Bering Strait. So to give you an example of this is now a sea level records, global mean sea level over the last 50,000 years, 3 canonical records here. We've got Fairbanks and Peltier in the black. This is the ICE 5G relative sea level model. We've got the Red Sea and the Mediterranean Sea from Grant et al. In the red. And then we've got a compilation of a lot of different oxygen isotope techniques for measuring sea level in the blue here. And regardless of what you see, sea level during stage 3, or in this period called before 35,000 years ago, was lower than the sill depth. And this is what I thought. And this is why I measured 3 cores, because I thought I'd like messed something up terribly. But it's not just one core that has this. Every single core we measured in the Western Arctic has this high delta-15 nitrate. And we cannot explain it coming from anywhere else in the Arctic. Again, the only other thing we have is this really low delta-15 nitrate Atlantic water, or we can have terrigenous inflow, which is even lower delta-15 nitrate. So we really cannot find another way to explain this. So this got me talking with Tamara Pico, who's argued pretty much since her PhD with Jerry Mitrovica that what we thought we knew about sea level during the stage 3 period prior to the Ice Age is wrong. And effectively, this is now a much broader compilation of sea level constraints over the last 50,000 years. You can see that everything agrees quite well from the last glacial maximum through the Holocene to today. And this is because this is where we have a ton of geologic evidence of what sea level change was like. But when we go before the last glacial maximum, it's very hard to get geological observations of sea level for 2 reasons. One, sea level is declining, which tends to not preserve geological markers of sea level. And in addition to the sea level being declining, ice sheets are expanding. So if we want to know how big ice sheets were, whatever their margins were then eroded by the growth of the ice sheet. Effectively, these triangles here are the only geological constraints we have on sea level, our gold standard constraints. These are corals. These are all from the Huon Peninsula and uplifted terrain in Papua New Guinea. Now, converting their modern elevation back to their paleo depth depends on what the uplift rate is. And what's happened, you can see the error bars, and these are quite big. The difference between these light-colored points here and then these dark-colored points is a change in the uplift rate calculation that's been done recently. In other words, everything's moving to higher elevations during stage 3 than thought before. We've also got these 2 models of sea level change. One is a GIA model, the other is based on ice margin boundary constraints, what little exists, both suggesting something like minus 30 meters GMSL during stage 3 instead of minus 90. And one thing I'll point out is that the range between minus 90 and minus 30 is pretty alarmingly big, right? That's the contemporary volume of all the ice on Antarctica today. If we melted all the ice on Antarctica, we'd raise sea level from here to here. Our job as paleoclimatologists and paleoceanographers is to reduce uncertainty. Granted, this isn't a warm interval in the past or anything, but this is a big uncertainty in our knowledge of sea level. And so as crazy as it was originally, I don't think it's too wild to use a nutrient tracer in the Arctic Ocean to essentially pick and choose between these different sea level simulations and see if we can get a better constraint on how sea level changed. Important thing about the Bering Strait is it's not some sort of beautiful tropical location far afield from any sea level change. It is in high latitude northern hemisphere. It's close to North America where big ice sheets grew and decayed. So it may be subject to crustal motion or glacial isostatic adjustment based on the growth and decline of those ice sheets. And this is where Tambra and Becca and their awesome expertise came in. What they did is they took 3 simulations of global mean sea level, or the ice history associated with that global mean sea level, encompassing the range of possible sea level that we see in the stage 3 period. So again, here a range of minus 100 to minus 30. And then what they did is based on where that ice was located on Earth's surface, they calculated the crustal vertical motion at the Bering Strait to get relative sea level at the Bering Strait. So this is global mean sea level. We can't assume that this dashed line, it works for global mean sea level at Bering Strait. We have to go to relative sea level. Now, fortunately, it doesn't make a big difference. Ultimately, if the strait did not change its depth going back over the last 50,000 years, then the only scenario in which we get the Bering Strait to be flooded during stage 3 is this really high global mean sea level during stage 3. So instead of minus 100 meters, something like minus 30 meters for stage 3. And this gets me geeking out a little bit, particularly with Danny, about thinking about the glacial cycle. So you've probably learned at some point the glacial cycles are sawtooth, right? There's a very slow inception and there's a rapid deglaciation. The sawtooth patterns of the 100,000 year glacial cycle world. And that's a lot of the evidence for that is based on something like, let's just move down here to looking at temperature change from Antarctic ice cores. You see it was very cold between 50 and 35,000 years ago. Got a little bit colder into the peak of the ice age, but the big thing that's happening here is the deglaciation, right? If we look at concentrations of greenhouse gases or the radiative forcing, also quite low during stage 3, get even just a bit lower during the LGM, and then a very rapid rise going into the ice age. But that's not what the sea level simulations that support a flooded Bering Strait show. In fact, sea level now looks much more symmetric around the ice age maximum than it did previously. So you have a relatively rapid growth of ice leading into the peak of the ice age and in about an equally rapid deglaciation coming out. And so this kind of leads to an interesting wrinkle that is, I know, driving Danny absolutely nuts right now, which is how do you possibly have this separation between, in this case, cooling and greenhouse gases versus ice volume? How can you, we think, as you grow ice has a very high albedo. That's a very important aspect of Earth's energy budget. So growing ice cools the planet, right? But we have cooling that existed before ice was very extensive. How do we do that? And I don't have an answer yet at this point. We're still thinking about this, but we want to raise this as an observation to think that, hey, the ice age cycle, at least in terms of ice volume, seems like it was much more symmetric than what has long been thought. Okay, last thing, and then I'll end here. I'd be remiss if I didn't talk about human migration, because having a proxy for the flooding history of the Bering Strait, flip that on its head, that means you have a proxy for the history of the Bering Land Bridge, because it's either a land bridge or it's a strait. You've probably seen some sort of National Geographic type cartoon sometime between 45,000 years